Thanks for coming to this talk. I'm David Moon. I just completed the first year of my PhD at the University of Colorado Boulder, and this is joint work with Cyrus, Omar, and Benjamin Shapiro. So today I'm going to tell you about our ongoing work on designing an efficient and easy-to-use structure editing experience. And the first question you might be asking yourself is, why am I talking about the usability of a structure editor at a workshop on type-driven development? So let's start there. One of the promises of type-driven development is that we encode varying levels of constraints on our program behavior in the form of static types, and in return, our editor can use those constraints to help us continue writing the rest of our program. Unfortunately, under the edit, compile, run loop of programming today, using a text editor, that assistance isn't always available. So when we write a program in plain text, it first has to undergo this gauntlet of transformations. First, we have to make sure that the program is syntactically well-formed. Then we have to make sure it's well-typed. And finally, we run the program. Hopefully, there aren't any runtime errors. And different editor services can be made available at each of these stages. As type-driven developers, we're particularly interested in those editor services that leverage type information at the typed tree stage there. But the problem is that our program often doesn't make it to that point. We might have failed to write a syntactically correct program. Here we have let x equals 2 plus and missing the right operand. Or maybe our program is syntactically well-formed, but it doesn't type check. Here because we have a free variable f. And so these two examples, they're pretty simple and they're fixed quickly enough, but sometimes these errors stick around for a long time. Say when we're pattern matching on large data types or performing a large-scale refactor on the program, and it may be that we run into some runtime error and we lose sort of the live dynamic behavior of the program as well. So the idea behind Hazel is to, rather than using plain text as the main input for our programs, we use type-aware structure editing. And what this enables is an always, like our editor services are always available. And so prior work on the meta theory for Hazel has shown that every edit state has a well-defined type, and it can also be run to produce a well-defined result. And the central idea the idea that's at the core of this, this invariant is this mechanism of automatic hole insertion. So I'll show concrete examples of what that looks like in a demo toward the end of this talk, but just to give you a little bit of a taste of like what is made possible by this sort of type structure editing experience. Here are a couple of figures pulled from the latest publication on Hazel. So here we're implementing a quicksort function, and maybe we've completed most of the body here. We've partitioned the quicksort around the pivot. We've recursively called quicksort on the two partitions, and then we finally have this final concluding expression to put back the recursive results together. And in this process, we can actually, these holes are in the evaluation, they're evaluated, the result is a hole closure, and we can interactively explore the environment that's captured in that closure. So if we start on the left here, here's a context inspector showing us the values in our environment at this hole 1. And we can see that smaller is set to be 231, bigger is set to 657. If we had, for example, maybe not exactly remembered how exactly the partition function works, and maybe we had actually accidentally reversed this sign here, then we would see immediately the result of that mistake, and we would be able to edit that, correct that mistake immediately, even when we don't have a complete program. Within this context inspector, we can further explore recursively the sub-instances of these holes that are in the recursive subcalls. And in this way, we get this very richly interactive experience. And again, all without ever having to leave our editor, switch contexts, without even having to complete the program. Here is another, say now that we've progressed a bit in our quicksort implementation, and we've stitched together the results of the two recursive subcalls with the pivot in the middle. And well, we have a type error here because this is an append operation and it expects a list in the middle. But we left out we didn't make that a list. And so this results in a type error, but we can still, the evaluation still proceeds around the hole. And if we look at the result, we can see that roughly we have accomplished the right thing. We just haven't been able to reduce past these little type inconsistencies in the result. And so this sort of dynamic feedback, so Hazel provides this sort of richly interactive experience by making sure that its programs are always well typed, and both this type information and this live dynamic behavior is always available. So let's take a step back and orient ourselves. So hopefully I've convinced you that type-aware structure editing is something worth pursuing as a better foundation for type-driven development. And for the remainder of this talk, I'm going to tell you about our ongoing attempt to design a usable structure editor. At the end of the day, an elegant meta theory means nothing if the user experience sucks. I'll start out by introducing the basic challenge of designing a usable structure editor, and also run through some contemporary structure editor designs to consider the different dimensions of that design space, and sort of the ways that these challenges have been addressed so far. And along the way, I also want to introduce and motivate some key features of Hazel's structure editor design. So we've already introduced the central feature of automatic hole insertion, and again, we'll see concrete examples of that in the demo toward the end. And in the next part of the talk, I want to introduce a few more important features that enable a smooth editing experience in Hazel. So keep an eye out for these purple tags in the next few slides. And I'll then give a demo of Hazel's structure editor in action on a few small programming exercises. And finally, I'll briefly touch on future work and conclude. Okay, so let's consider a simple structure editor. In this structure editor, the cursor selects a subtree in the syntax tree and edits our context-free tree transformations of the cursor subtree. So let's say we want to construct the expression 2 times 3 plus 4. And we start with 2, and the cursor is on the node 2, and we press times. The times operation, it applies a transformation to the current node where it pushes down the current node to the left operand of the times, and then it inserts a syntactic placeholder on the right and moves our cursor there. We now press 3. 3 takes the place of the syntactic placeholder, and then we press plus. Well, okay, so this isn't quite what we wanted. Our structure editor blindly applies these context-free transformations. So again, it applies that operation of pushing the node down to the child and inserting a syntactic placeholder to the left or to the right and moving the cursor there. So, but yeah, this isn't what we want, so let's backtrack. So this is where we started, and what we actually need to do first is we need to navigate up to select the parent subtree, and then we can press plus and then 4, and we get the expression that we want. So fundamentally, there's nothing wrong with this sort of interface, but culturally, we're so accustomed to this sort of sequential linear input and relying on operator precedence to take care of the associative structure for us. In our sort of, I think in order to design a structure editor that is sort of aligns with our current cultural values, we really need to support this sort of linear editing affordance, sort of a text-like editing experience that takes into account things like operator precedence. So prior structure editor designs acknowledge this requirement for a usable editing experience. The Cornell program synthesizer is one of the first structure editors created in the 80s by Teitelbaums and Reps. And the way they handle this issue is they just relax the structure editing requirement at the expression level. The higher level statements and the control flow constructs, these have to be inputted structurally, but at the leaves you can enter text. And later designs employ sort of like an online precedence parsing idea, and this is what we do in Hazel as well. So I wanted to go through this example. It's very simple, but it demonstrates a fundamental tension that has to be handled by a usable structure editor. The tension between this desire for linear sequential editing and the tree structure of what we're actually manipulating. So if we explore a few, so if we look at a few contemporary structure editors, say today's like state of the art is MPS, JetBrains metaprogramming system, and they have fully embraced this idea that structure editors need to be text editor-like. And so on the left is what it kind of looks like to write programs in MPS. And overall, the experience is very close to text editing. Expert users are very efficient, and MPS is used in professional development settings. But despite this, there's still this learning curve to MPS. In the end, the interface is not the same as text editing. So if we look at this figure here, this is a figure taken from a controlled user study by the MPS team. And we have here 3 user groups. First, the user group is novice users of MPS who are presented exercises in MPS, are interacted with MPS for the first time, and solved a series of exercises. And then we also have MPS experts who are solve the same exercises. And then as a control group, we have a group of programmers who did the same exercises but using a text editor. And I think I want to draw your attention to these particular 2 subplots here. So if we look at selection first, we see that the beginners, they kind of have trouble with selection, but eventually the experts, they kind of figure it out and they know what they're doing. But I think this deletion subplot is particularly striking. Both the beginners and the experts don't feel that confident about how deletion is going to perform. The MPS team, they acknowledge that in the end, MPS is not a text editor. There are points when you need to know about the tree structure to be able to predict what's happening. So I think the sort of main usability issue here is that this tree structure is not visible to the user in this goal of like reaching text editor-like this text editor-like interface. Scratch is another contemporary structure editor, and it sort of has the opposite issue. So it uses this block-based interface where you can snap together blocks to form programs. And here, the visual tree signifiers are persistent and always available, but you have no efficient linear editing affordances. And so as a result, so these blocks take up lots of screen real estate. Clicking and dragging is cumbersome, so it's not great for experts. Lastly, I want to touch on the last feature of Hazel, which the last feature I've mentioned about Hazel, node staging mode, which is just briefly to motivate it, we've seen lots of prior work has paid a lot of attention to like linear editing of infix operator sequences, but there hasn't been a lot of similar attention paid to other syntactic constructs. And so this mode is our attempt at solving that problem, and we'll see it in action in the demo. So why don't we hop right to that. Okay, so this is Hazel. This is a Hazel cell, and here we're expected to fill this Hazel cell with an expression. We haven't provided that expression yet, so we just have an empty hole, an indexed empty hole there. And so if I just start typing, actually, sorry, in the interest of time, I'm going to actually just move on to the next example. So here is our familiar map function. And so if I move around, you can see that anywhere that the caret is, there is an associated box that is like a light green shading. That's kind of hard to see here. But the light green shading indicates the current node that's selected. And then there's also these two lines that indicate the current term or current expression. So the rule by itself doesn't form a valid expression, but in the context of the case, it does. So I can move around, do that. Here in Hazel, I'm only using alphanumeric characters, arrow keys, backspace, and tab. So I can, so if I start typing out this example here, I've disabled the live the live computation for now, just to focus on the structure editing. But here we see that Hazel has automatically inserted this free variable hole. And if we look at the cursor inspector up on the upper right corner, we get this information at all times. And yeah, so okay, so that's a quick introduction to the cursor indicators that we've provided for Hazel. Let's step through this sample exercise. So let's say we're implementing this function called damage that takes a tuple that is, let's say we're defining this damage function that takes an attack tuple that is a Boolean that represents whether the attack is a melee attack. And then we also have this critical hit multiplier. And so depending on whether it's a melee, we assign different damage points. Here for true, we might say multiply crit hit +1. And here, again, we see this, that the cursor indicators provide this nice information about the operator precedence here. And I'll tab to the next hole. And now let's say now that we want to do some refactoring and we want to actually take into account this defense score variable into the calculation of our damage points. And in particular, I want to say that make this its own, encapsulate this in an attack score variable, and then return twice the difference between defense score and attack score. So I can just insert a new line. We can insert new lines. Sorry, let me skip over that. And so I'll define a variable called attack score here. And now I want to actually put this case expression into the defining body here. So what I can do is I can just go, if we think about how we might do this in a text editor, we backspace on the n, we're going to go down around the case and then reinsert the n. Well, similarly, what we can do here is we can hit backspace, and now we've entered node staging mode. So we've taken this let line node, and we're taking this delimiter, and we're shifting it to different viable positions. So here we can now shift it down and press enter to accept that. And then finally, we'll do 2 times attack score minus defense score. But then I've forgotten about operator precedence. So again, I'm going to parenthesize this here. And then I'm going to backspace here, and I can just shift it over. And I've gotten that. And yeah. And just briefly on